All right, in this video, I'm going to go over section 5.3, joint probability distributions for more than two random variables. So simply saying that the joint probability, let me say just joint PDF, okay? PDF more than two random variables is just extension of joint PDF with two random variables. Okay, so just you can see that more than two random variables can be defined in a random experiment. Result for multiple random variables are straightforward extensions of those for two random variables. So let's take a look at the formula of joint PDF for more than two random variables. See x1 through xp, these are the multiple random variables, okay? And then that's the notation of joint PDF. See, definitely the joint PDF for more than two random variables must be greater than or equal to 0, and the formula is this: the multiple the indefinite integrals of that joint PDF, right? That must be equal to 1, and then the probability that multiple random variable belong to the certain the reason B is going to be, that's the multiple. This, you see that here the two integrals notations, but that's not the that doesn't mean the double integral. Okay, that must be the multiple integral, because B, see, for any reason B or P dimensional space. So this is going to be P integrals. Okay, so now then see example 5.11, machine dimensions. Many dimensions of machine part are the routinely measured during production. Let the random variables x1, 2, 3, and 4 denote the length of four dimensions of part. Then at least the four random variables are of interest in this study, right? So now then let's say typically that joint the PDF with p random variables define the overall of p dimensional space by assuming that the that joint the PDF equals 0 for all points for which this is not specified. So the think about this. When we study the joint the PDF with the two random variables, okay, and then this, if that joint the PDF was 0 outside the domain which define the function, right? So similarly, we assume that joint the PDF with the p random variable equals 0 outside of the domain. Okay, in this case, domain is not going to be just the region in two-dimensional space. It's just kind of certain, yeah, maybe polygon, I don't know, certain region in p-dimensional space, right? It's kind of hyperspace. So that outside the domain, that in the outside domain, that joint the PDF gonna be 0. That's what we assume. Let's see example 5.12, component lifetimes. In an electronic assembly, let the random variables x1, 2, 3, 4 denote the lifetime of four components, respectively. In ours, suppose that the joint PDF of this variable is this, okay? As you can see that this is actually, I mean, in a view of calculus, this is a function with four variables, right? X, Y, Z, W, something like that, right? So anyway, so the four random variables involved here, you see that? Okay, so what is the, but definitely this is greater than equals 0. We see that e to the something exponential function is always greater than or equal to 0. Actually, always greater than 0, right? For any choice of value, a random variable, okay? So yeah, makes sense. And then so it's the x1 is greater than equal to 0, x1 through x1 through x4 are greater than equal to 0. That one give us the that one give us what the what does domain look like, right? Okay, so this one what determine the domain of that joint PDF. Okay, what is the probability that the device operates for more than 1,000 hours without any failure? So the requested probability is this. The more than see the more than 1,000, it means that what we need to find the probability that x1 is 1 through x4, all 34 variables are greater than 1,000, right? So which equals the multiple integral of f that join the PDF over the reason. Okay, so that means what? The joint probability density function can be written as product of exponential function, and each integral is simply integral of exponential function. Therefore, this. So what that means, I'll show you why this is equal to this in a skyscraper. Just give me a second. All right, so let's see. This is solution of example 5.12 components lifetimes. So so the question is to figure out the probability that the four the random variables is represent the lifetime of the four components is or great each component is greater than 1,000 hours without any failure. Okay, so to figure out that probability, then we need to calculate the multiple integrals because this is PDF with four random variables, right? So starting from this, but since that joint PDF is defined on the reason and such that x sub 1, x sub 2, all four variables are greater than or equal to 0. So that, you know, the lower limit, upper limit for integral will be reduced by 1,000 infinity. See that 1,000 infinity, 1,000 infinity, 1,000 infinity, right? And then see that here, that joint PDF is what defined by in the problem. In the problem, they define that a joint PDF as 9 times 10 to the negative 12 times e to the negative 0.001 x1 through this. But it's, you know, exponential functions with the some of the exponents can be rewritten as like this, the product of the exponential functions. Okay, see, I just used the law of exponent. Okay, so now then it's each exponent involve only one variable for each x1, x2, x3, x4. It means that we can break up that multiple integral as product of four integrals like this. The one, see, this is integral with involve one single random variable. Okay, so this is integral of x1, integral of x2, integral of the x3. This integral of the x4. Okay, so I just break up that multiple integral as product of four integrals with single variable for each. And then the constants I just brought out of integral 9 times 10 to the negative 12. Now it's that these are actually what in-depth integral. I believe that you learned the calculus too. Okay, so since it's an infinity is involved, so these are in-depth integral. Then how can you evaluate? Then we need to use the concept of limit. Okay, so we replace the infinity as the finite number. T represents finite number, and then we evaluate limit as t approaches infinity. Okay, so limit of these product of those four integral. All right, now since these are not in-depth integral anymore, so we can consider that these are just depth integral. That we use the using the EPIS part 2, fundamental theorem calculus part 2. We can evaluate these are. So let's just figure out, excuse me, the limit of that integral. Okay, so then the limit of this integral with the random variable x1. Then entire derivative of the that one integral e to the negative 0.001 x1 is this e to the negative 0.001 x1 over negative 0.001. I believe that you can do by yourself. Okay, you know how to find out the entire derivative, right? So now, and then we evaluate this entire derivative, t and 1000, and then take a difference, right? So we got this. But see that here, e to negative 0.001 t. This is decreasing functions. Graph of this one is this. never touch the horizontal axis, t-axis, but approaches 0. Okay, as t approaches infinity, so it means what? Limit this one approaches 0 as t approaches infinity. So we this one approaches 0. So this is gone. That term is gone. So what's the remaining term? This e to negative 1 over 0.001. Similarly, we can figure out the rest of the integrals with the limit is like this here. Okay, so look at the bottom one: 0.001, 0.002, 0.005, 0.003. The product of those four denominators is equal to 9 times 10 to 12, negative 12. So we just cancel them out. Okay, so now then what? So the answer is what? E to the negative 1 minus 2 minus 1.5 and minus 3, which is e to negative 7.5. But the example in the textbook, they just express this one as a decimal expression, 0.00055. Okay, so that's a solution of example 5.12. All right, so okay, we just saw example 5.12. So now you know how to calculate how to find the probability involved in multiple random variable, right? So now see that some kind of special case. Suppose that the joint PDF of several continuous random variable is constant C. Okay, so what if joint PDF with a multiple random variable is defined by a constant C over region R? Okay, that's just domain. Okay, then the probability on that region R is just nothing but C times the constant C, which is the value of joint PDF at any values of random variable, okay, times volume of region R equals 1. I believe that you have seen this one in calculus. Maybe you will, okay, in calculus 3. Okay, so then now what if we just joint PDF is defined by C, but we want to find the probability, not the domain R, region R, but just subset of R. Let's say B. B is a subset of R. Okay, then we're gonna, this is equal to C times the, see that, intersection, okay, of volume B intersection R. Okay, so that is equal to volume B intersection R over volume R. Okay, so that's the similar to what we haven't seen in our property 3 equation 5.9. Okay, so now example 5.13, probability is a ratio of volume. See one more example. So suppose that the joint the PDF for the continuous random variables x and y is constant over region. This the x squared plus y squared is less than y equals 4. That's the what? The circle, right? So domain of that joint PDF is a disk with the radius is what? 2. Determine the probability that x squared plus y squared is less than or equals 1. Okay. So now then what? The region, so we're gonna use what? Figure out, see, second, we're gonna use this one, okay? Because x squared plus y squared less than or equals 1, that region is the what? Kind of subset of that region, right? Okay, part of that region. So the region that receives a positive probability is a circle of radius 2. I told you. Therefore, the area of this region is 4 pi. Pi r squared. That's the area of the circle, right? Therefore, the area of this region is 4 pi. Okay, the area of the region x squared plus y squared is less than or equals to 1 is pi. Yeah. So consequently, the requested probability is the volume of intersection of two regions divided by volume of the domain. Okay, so which is pi over 4 pi, which is 1 over 4. Okay, so this is really the good useful trick. Okay, you don't have to evaluate integrals. Okay, as long as if the joint PDF is defined by this constant, you don't have to evaluate the integral. Okay, now let's see marginal probability. Marginal PDF. If the joint PDF of continuous random variable x1 through xp. The let me say just MPDF, okay? MPDF of xi is this. So this is pretty much just straightforward extension of MPDF of two variable. Okay, so the now we to see that that's the MPDF. Sorry, just PDF, right? But the integral is what? It's not just p times integral. Okay, just p minus 1. Okay, x1 through the xi minus 1, and then we skip the dxi. Okay, and the dxi plus 1 through xp. So now let's see, as for two random variables, the probability involving only one random variable, for example, probability that xi is between a and b, can be determined from marginal PDF of xi or from the joint PDF x1 to xp. Okay, that means you see that probability that find the probability that xi between a and b, we have to consider all of the variable. I mean the all of the possible values where xi is between a and b. It means that x1 through the xp except for xi, when you calculate probability, their inner must be negative infinity infinity. I know it's kind of confused, but let me see. Let me see example 5.14 and then back to the mean and variance of joint PDF. Okay, so look at this. Points that have positive probability in the joint PDF probability distribution of two random variable, okay, are shown in figure 5.10 right here. Actually, this is a PMF, right? So this will deal with discrete random variable. Suppose the 10 points are equally likely with a probability 0.1 each. The range is the non-negative integers with x1, 2, 3 equals 3. So all 3 points are these points satisfy this x1 plus 2 plus 3 equals 3. Okay, the marginal PDF of x2 is found as follows. Okay, so now margin, let's find out all possible cases of MPDF of x2. Then x2 can be 0, 1, 2, 3 because x1 plus 2 plus 3 equals 3. So to set these are cases that that sum of 3 random variable equals 3, right? X2 cannot be 4. Okay, so x2 cannot be greater than 3. I mean, okay. So let's look at this. Probability x2 equals 0. Then what? We need to find out all points whose x2 value of x2 equals 0. Okay, it means that what? The points must be lie on the x1, x3 plane. Okay, so every single point on the plane x1, x3 plane, their second coordinates, which means that the value of the x2 must be 0, right? So we see that here, this one, that, and this. So these 4 points lies on the x1, x3 plane. So we're gonna find out the what value of the PDF, actually PMF, right? And then we're gonna add all values. Okay, so you see that f of x1, 2, 3, 3, 0, 0, which is this, that one, 3, 0, 0, and then 0, 0, 3, 0, 0, 3 right here, and then 1, this is 1, 0, 2, and then this is a 2, 0, 1. Okay. So now, since the suppose the 10 points are equally likely, so the point is 1. So value of each PMF gonna be 0.1. So 0.1 plus 0.1 plus 0.1 plus 0.1 is 0.4. Similarly, you can find out the other marginal PDF of x2. Okay, so that's the meaning of this. Okay, so that's the meaning of that one. So now let's see mean and variance from of joint the PDF with a multiple random variable. So this is also straightforward extension of joint the PDF of two random variable. Okay, so xi times e of xi is just the multiple random variable with xi times PDF. Okay, so but this is what not this can be expressed as what the marginal PDF of xi, right? And then variance is xi minus mu xi. Mu xi is the e of xi, okay? Square times the PDF, okay? So this one can be expressed as the what? Margin integral of xi minus mu xi squared times marginal PDF of xi with respect to xi, okay? So that this is also a straightforward extension of the PDF with two random group. Okay, so now next one. So let's see, with the several random variables, we might be interested in a probability distribution of some subset of collection of variable. So the probability distribution of x1 through xk in the case less than p. Now you see, we're gonna consider the just some kind of part of the random variables, not x1 through xp, okay? x1 through the xk in the case less than p, okay? So that's the meaning of this, some subset of collection of variables. Can be obtained from the joint PDF of x1 through xp as follows. Okay, distribution of subset of random variables. If the joint PDF of continuous random variable x1 through xp is this, the probability density function of x1 through xk is this. It's kind of straightforward. So you see, now this is a what? Not the p times integral. Okay, this is this. Yeah, definitely multiple integral. But how many integrals here? This is it. These are integrals with respect to xk plus 1 through xp. And then this is just a joint PDF of x1 through xp. Okay. Right. So where the integral is over all points are in the range of x1 through xp, for which x1 is x1, x2 is x2. See that? So that's the what? x1, I mean, this is the joint PDF of some subset of collection of variable, specifically random variable x1 is equal to lowercase x1. Okay, I told you it's just lowercase represents specific value of random variable. Okay, the capital letter represent random variable. Okay, it's a variable. Okay, so we want to find out probability. Okay, that first random variable has the value x1, second random variable has value lowercase x2, through the kth random variable has value lowercase xk. That how can you figure out that probability? Just we take an integral of joint PDF with respect x of k plus 1 through xp. Okay, so now let me see. Second, now we see conditional probability distribution. The conditional probability distribution can be developed for multiple random variables by an extension of idea used for two random variable. Yeah, so say we just figure out the conditional probability of x1 to 3 given that x4 is x4, x5 is lowercase x5, okay? Then that is equal to join the PDF of x1 through x5 divided by, you see that that's the marginal PDF, okay? See that? So and the independence. If random variables are independent, the joint PDF can be expressed as a product of joint PDF with a single random variable. And this is really nice, right? So that's the 5.3. Okay, so most of the formulas are just straightforward extension of joint PDF to random variable. So I don't think you're gonna have a big trouble to understand this stuff. So let me stop here.